Hello everyone, hope you're doing well. Welcome back to my channel. Today we are at day 4 of the April Daily Leetcode Challenge, and we have a medium question now. And from today onwards, we are going to enter into the topic of trees basically, and especially today we have the question on binary trees. It's a very good and old question, so please do try it out once before seeing the video. It's a very nice one, and believe me, it is something very generic that you can definitely expect in an interview because this will be the first starting level of question that you will be getting in an interview. Okay, because it's like totally it will test your basics in the tree topic. Okay, so coming to this question, it talks about the lowest common ancestor of deepest leaves. Okay, so the question makes it very clear. I'm not reading this part, so these parts are just for your information. Okay, only the last line is of use to you, and obviously the main statement is of use to you. So only read these two things. If you're not aware of other stuff, then maybe go and read this out. But only two things that you need is this particular statement and this particular statement. Okay, and then we'll see one edge case, and then we'll go to the code directly. Okay, so here the question talks about the lowest common ancestor of deepest leaves. So if you see the example number one, basically in this case, first of all, I'm assuming that you know what is a binary tree. You know various definitions and terms specifically being used with the which are being used with the topic of trees. Okay, for example, first thing is depth. Okay, node. I think you know that each that circle that you're seeing is a node basically, and the depth topic. Okay, what we here they are saying that the depth of the root will be zero. What that means is depth means, as you know, depth basically means like how much deep you can go. Okay? A measurement of the depth, how much deep you can go. So in this case, if you see threes at zero means five and one. Okay, five and one that you're seeing, these are even one level below the root. Okay, so we'll say the depth for this is just plus one of the depth of three. Okay, so threes are depth zero means five and one will be a depth one. Okay, similarly six, two, zero, and eight. Okay, they are at the same level. Okay, level is again a technical term that we use with reference to trees. So here, if you see six, two, zero, and eight are at the same level, and in this case, they are at the depth of two. Okay, because there are two I can say like two edges below the root. Okay, as simple as that. It will take two edges to travel to any node from 6 to 08 from 3. Okay, simple as that. And similarly, if you talk about 7 and 4, it will take three edges basically to reach 7 and 4 from the root. Okay, so you have to go from 3 to 5 to 2 2 and then 7. Okay, so it will take three edges, so you can say the depth of the hit is going to be 3. So in this case, as you can see, 7 and 4 are going to be the deepest nodes, and for them we basically need the lowest common ancestor. So what is the meaning of lowest common ancestor? See, if we talk about common ancestor for 7 and 4, can you quickly tell me what are the common ancestors for 7 and 4? Obviously, it is going to be 2, 5, and 3. Do you all agree with me, first of all? Common ancestors for 7 and 4 are going to be 2, 5, and 3. Okay. Now the question is lowest common ancestor. So what is the meaning of the term lowest? See, lowest is again with the reference to the depth. Okay, so we have to, among all the ancestors, we have to see which is at the max depth. Okay, so among 3, 5, and 2, obviously 2 is at the max depth. So in this case 2 is going to be the answer. There is a one very tricky part here, because if you read this part, okay, if you read this statement, if you interpret, see again, like seeing example number one, if you read this you may not get much idea, but if you read this particular statement that I've highlighted after going to example number 2, you will get another insight here. They are saying that if there is a single deepest node, then in itself it's going to be the LC. Okay, it is going to be LC of itself. Okay, what is LC? LC is going to be the lowest common ancestor. Okay, so in this case, let us say 7 is not there. Okay, just to try to understand, like imagine this example. Let us say 7 is missing from this. Okay, so the deepest node is going to be 4. Okay, now since deepest node is 4, it is going to be, see, every node is first of all a parent of itself. Okay, we can say it like that. Okay, in theoretical terms, every node is going to be a parent of itself. Okay, so it will be in its own subtree kind of, we can say. So if you now take this definition and try to apply here, it will be applied basically. And what we can conclude is, if there is a single node which is at the longest depth, at the max depth, then for it is going to be the LC. Okay, lowest common ancestor. It is going to be its own parent, so it is going to be its own ancestor. Okay, as simple as that. So it will be the lowest common ancestor for itself. So this is one edge case that you have to remember. So for any scenario where you have only a single node at the deepest level, deepest depth, then we can say that it is going to be LC of itself. Okay, and same is the case here for 2 also. It same is the case, and similarly here for 1 also it is the same case. Okay, as simple as that. Right, now let us see how to approach this problem. So I have done very basic work. I'm not doing anything extraordinary, but still the code that I've written, it will be solving, it will be taking at 3 milliseconds, 3 to 2 milliseconds every time. Okay, when you segment, you can see it. So again, at the starting step, I'm mentioning this part of the code that we're seeing is just the optional part. If you want, to return it. If you don't want, you can even skip it. Okay, this is specifically taken for the case we have in example number 2. Okay, it's specifically for that. Okay, because here, if you see, only single node is there in the whole tree. Okay, so the answer is going to be the node itself. Okay, this is for this case basically. For example, specifically we have this, but again, this is optional case. I mean, you can remove it. The code below it again handles the same, but in a longer way. Okay, this is the shortcut to handle that. If you want, you can have it. If you don't want, you can remove it also. Okay? It's up to you. Let me comment it out for now. Okay, I am commenting it out, but if you want, you can have it also, right? It will, for some cases, it will it will be basically shortening the actual process that you're doing. Okay, now how to do. The first thing that I can think of is, when I see this question, is, first of all, before doing anything extra, anything more, what I need is, I need to know the max depth. Okay, that is going to be my approach. So first of all, before doing anything else, I'm going to create a variable to show the max depth. Initially it will be 0. Okay, remember the root is always at the depth of 0, so that's why I'm starting this with 0. And then I'm creating a function. It's going to be a recursive function. Basically, it's almost like a dfs. You can say it's a dfs only, but just to match the case it is solving, I've given is the name of find max depth. Okay, so when I call this function, okay, with the root as the parameter, what it will do is, it will update this particular variable. Okay, and at last, when this function completes, basically all the recursive call of this function completes, in this particular variable I will have the max depth. Okay, so first I will show you the output of that, and then we'll go to further. Okay, we'll move further in the code. Okay, so just let me explain on this part. So this is going to be recursive function. What recursion means? Recursion basically means that, as I mentioned, it's analogous to defs. Okay, what it means is, it will be calling itself. Okay, in this case, if you see what we are doing, we are passing a root as the parameter, and the other optional parameter is depth. The default value for it is going to be 0. Okay, so if you don't pass any value, like we have done, see, this is the first function called this. Okay, yeah, this is the function, and okay, the function is ending. This is the function basically, and this is the function called to this function. We are not passing anything other than the root, so this particular depth will be 0 initially. Okay, now what is being done is, if root is none, return, don't I mean simply return the function. Don't return any value as such, but simply return from the function. Then it will just check max depth is equal to max of the previous value of the max depth, current, comma, the current depth of the node. Okay, and similarly it will call the same function for its root. Okay, I will again repeat. See, it's just a simple defense function. If you have seen the defense functions previously, you will find it very relatable. We are not doing anything extra here. Basically, only additional step that I'm adding is this part. Okay, for every node that we see, idea here is same. We are visiting every node. Okay, in a DFS way. Okay, what is DFS? It's a depth first search. That is, we will cover whole depth first. Okay, for example, if we start from 3, okay, then the whole line towards the left will be covered first. Okay, that is, from 3 we'll go to 5. From 5 we will go to 6. Now see, there is no more left nodes left. Okay, there is no more left nodes remaining. So now we will backtrack. We'll go to 5, and then we'll go for the first right node. Okay, so first all the left nodes will be covered to the extent possible, and then we'll go for the first right node, and so on. Okay, so in this case, that's what is happening. If you see, we are calling the left, we are exploring the left subtree first. And see, the idea here is, we are going through each of the nodes. Okay, the way that I mentioned, all the left node will execute it first, and then the right nodes. Okay, but idea is the generic idea is, we are going through each node, right? Now, when we are at each node, what we are doing is, we are also doing this part. Okay, whenever we are going from one node to another, we are increasing the depth. Okay, as simple as that. So whenever we are at a node, at a valid node, what we are doing is, we are trying to capture its depth. Okay, so at last, when this whole function completes, all the regression completes, yeah, this whole basically completes, we are now going to print the max depth. Okay, let me show the outputs first. See, this is the example number 1. Okay, here the max depth equal to 3. So if you see, in this case, 7 and 4 are actually at depth 3, right? So 3 is 0. Okay, 5 is 1, 2 is 2, and 7 and 4 are 3. Okay, they are the depth 3. So this is correct. If you go for example number 2, the depth is going to be 1. Okay, and similarly, if you go for example number 3, in this case again, the depth is going to be 2. Okay, as simple as that, right? Now this part I hope is clear. It's very pretty simple. I've not done anything extra, or anything too much algorithmic. I've just done the basic part. I'm calculating the depth first. Okay, now we'll go for the actual problem. Okay, now we're trying to solve the actual problem. So first I will make the answer equal to -1. Okay, and then we are again going to do the same DFS, but in this DFS we are going to be mindful of the fact that we need to find the lowest common ancestor. Okay, LCA, right? The lowest common ancestor. But like, see, what logic that we're going to apply now. See, the idea is going to be very simple. Yeah, see, whenever we are at a node, we will know 2 parts. Okay, we will know, like, what are the its left and right subtree. This is the first thing that we'll know, because in the each node is basically going to be object of this class, so we know, like, what is the left and the right subtree. Another thing is, since the way that I've implemented it, if you see, at each level basically we are also going to know the depth of it. Okay, because that will be passed in a recursion parameter. Okay, the recursive function will have that a parameter that will tell us for the current node what is going to be the depth. So idea here is, for each node we will be knowing the depth. Okay, and obviously we also have the value of the max depth. That is, whenever we are at a node, we can check whether this node is going to be the leaf node at the max depth or not. Okay, so in this case, only 7 and 4, for only for these two nodes, that's a condition we will do that. Yeah, they are in the max depth. So idea here is, see, whenever, okay, let me zoom in and let me show the idea. Whenever we are at the max depth, okay, so whenever I'm at a node which is at the max depth, what I will do is, first of all, I will make the answer equal to the road itself. Okay, and then I will return the max depth. So I please try to understand the part. This part becomes very important for the case that we have in example number 2. Okay, that is, if let us say only single node is present in the max depth, then it is going to be the answer of itself. Okay, so that's why I have done this step first. Okay, believe me, this is going to change. This will not remain like that. Answer will change after that. Okay, when it will change, see, if there is a single node at the deepest level, this will remain the answer. If that is not the case, then it will change. How to change that? See, it is very simple. See, this you have to understand how the recursion is progressing. Okay, when we're at 7 and 4, ultimately, then we are going to backtrack. Okay, we are ultimately going to reach 2 again. Okay, see, from 2, 7 is being called, then we will return back to 2, and from 2, 4 is being called, and then we will return back to 2. So idea here is when we are at 2, after exploring its subtrees, we will basically know what were the depth of its subtrees. Okay, so that's what we are going to use now. If you see what we are doing, this is the defense function that I created. In this case, if you see what I'm doing, first of all, this is the terminating condition for the recursion. If the root is none, return -1. This part is again very, very important, because see, if you like basically analyze this whole code, no, at a time only two things will happen. Okay, either -1 is being returned or the max depth is being written. Only these two things will be flowing back. Okay, if you imagine what is being flown back or what is being written by each of these functions, each of the function calls, basically it will be either -1 or the max depth. Okay, because if you see, only these two values are being returned. Okay, after that, we are only written the max of them. Okay, so only like see this max is basically calculated value. Okay, if you don't go for the calculated value, only these two values are being written at every instance. Okay, either the max depth or the -1 value. Okay, now see this part. So these are kind of acting as a terminating conditions. Okay, I will come to them later on, but before that, let me show the code. So what I'm doing is, at every node, what I'm doing is I'm calling the defs. Okay, I'm passing the left node, basically left whole subtrees root I'm passing, left node I'm passing, and then I'm increasing the depth. Okay, this will basically return. Okay, this will return a value that I'm calling it as k1. Similarly, doing the same thing for the right subtree. It will return, it will return a value that I'm calling as k2. Okay, if k1 is equal to max depth and k2 equal to max depth, that means we have reached a node. Okay, we have reached a node which is kind of ancestor to nodes which are at the deepest level. Okay, I will again repeat. If this condition is true, that means the current node. Okay, for example, the node 2. No, for the node 2, this condition will be true. Okay, for the node 2, this condition will become true, because the return value from its child nodes are indicating that this is going to be a ancestor for the deepest nodes. Okay, so this condition will become true, and what we'll do is answer is equal to root. So this root is basically representing 2 in this case. Okay, simple as that. Then this will change. Okay, initially it was like this, now it will change, and now see, initially answer will be pointing 7, then answer will point 4, and then answer will point 2. Okay, so 2 will now be the basically the our answer, and we are going to return 2. When I say 2, I mean to say the whole subtree of 2. Okay, this being going to return is will be written as answer. Okay, fine. Now, how to progress? See, this is not the only question, right? Let us say 7 and 4 are there. There may be more than two nodes also which are at the max depth. In that case, what will happen? Okay, that means they may not have the, see, here that their direct parent is their lowest common ancestor. Okay, but this may not be the case always. Okay, I've seen there are multiple test cases where, let us say 7 4 have a single parent, but after that, let us say the 0 that you're seeing, let us say it also has some more values like 10 and 11. Okay, so in this case, they are also at the same max depth. Okay, so the lowest common ancestor in that case will be 3, right? How to do that? For that reason, what I'm doing is I'm returning this. Okay, so see what is being written. Only three things are being written: either this will be written, or this will be written, or this will be written. Okay, so in this case, if you see, if this condition becomes true, we are good. Otherwise, what will happen is we are going to return the max of these two. Okay, so in most of the cases, one of them will be -1. Okay, and the other one will be max depth. Okay, so we are going to return only the max of these two values. Okay, if one of them is -1, they will be ignored, and only the max part will be returned. Okay, as simple as that. So remember, only when this condition is so, we'll update the answer. Okay, as simple as that. So this condition will become true only if the node is going to be a common ancestor. Okay, so this basically condition, this is the condition in which we are checking if a particular node is a ancestor or not. Okay, as simple as that. And now your question will be how to identify the common, like the lowest common ancestor. See, the idea is going to be very simple here. Lowest common ancestor, for example, see, two. In this case, if you see, this condition is being satisfied only for 2. Okay, no, none of the other nodes are having this condition satisfied. Similarly, this condition will be satisfied only for the those nodes which are at the common ancestor, and obviously the lowest common ancestors. Other than them, this condition will not be true for any other node. Okay, as simple as that. So yep, yeah, friend, that was all for this particular video. Okay, and yeah, if you see, we are finally calling this function, and this is being called, and finally we are returning the answer. So this was my solution, and you can go through the sample test cases. There are some very good test cases basically in this question. Try to solve it out. See, I've given you the basic idea, I've given you the code also, but again, I don't expect you to copy the whole code. I expect you to understand the logic. Try to have some, take a pen and paper, draw back and see what values are being returned, why this code works, and then develop an idea, develop some extra test cases, develop, like, I mean to say, like, try to optimize this further, and then start coding, and then get your solution. Okay, I don't expect you to copy everything, but what here I expect is that I explain the problem to you. If you have not understood before, now you will understand it, because now I have explained even the edge cases, like we have in the example number 2. Okay, I explained those part also, so you will not waste your time in debugging a solution which is not going to work for this kind of cases. Okay, as simple as that. So yeah, that was all for this particular video. I will give this solution in the comment section. You can go through it and let me know if you have any questions. So yeah, that was all for this particular video. See you tomorrow. Thanks a lot.